Up to 11. It really is time. It's fantastic.
Thank you very much indeed, both of you. Back to you, Michelle.
Thanks, Katie. It is so great to have you and your colleagues with us on this historic day. So before we get to the fifth and final image reveal of the day, it cannot be said enough that an achievement like the James Webb Space Telescope is something bigger than any one of us. It's bigger than any organization, any country. This truly takes a planet. Webb belongs to all of us, and starting today, the discoveries start and are not going to stop. This is just the beginning. We've said several times throughout the broadcast that the Webb mission is about people, and during the construction of the Great Telescope, people started to see themselves in it, literally. Day after day, people visited the observation window at NASA Goddard, and looking through the glass, they snapped selfies of themselves reflected in the gigantic golden mirror. These photos are actual reflections of the enormous human investment and the emotional commitment that brought this mission to life. And now, years later, that mission is finally collecting light from the earliest days of the universe, all the way to worlds in our own solar system.
Skywatchers,
it's the same mirror that reflected the many faces who see themselves as part of the journey to understand our shared origins.
And you've got a front
Let's stop for a moment
to the
and appreciate the people behind Webb. Okay, it's time now for the last image to be revealed. I'm Michelle Thaler, your host for what can only be described as a celebration for everyone on Earth. To think about this, light from the earliest days of the universe has been traveling to us for billions of years. Just over the last few weeks, we've captured some of that light with a telescope that sees the universe in an entirely new way. And today we share the very first results. So longtime space fans are going to know. So Amber Strawn is Dr. John's deputy project scientist. He's here with me today to share the final big reveal of the Nobel Prize winner. So Amber, it's so good to see you. How are you feeling? Here with you today.
So great, so exciting. What a great day this is.
How are you feeling? So one of the things that we're going to do is before we get to the final image, the James Webb Space Telescope has taken us all over the universe today. So let's do a quick review of where we've been so far.
We are so proud.
So James Webb got us rolling today with an extraordinary new deep field image, showing us one of the farthest views of the universe ever.
We had just finished measuring the Big Bang.
It really does demonstrate that JWST can do exactly what we've designed it to do.
Goddard.
Yes.
And we measured
the Canadian Space Agency then took us to the massive planet WASP 96b, where the team has detected evidence of atmospheric water.
And here again, we're seeing the incredible efficiency of this observatory. We're able to do these kind of measurements in a fraction of the time that we were able to before.
What happened after the Big Bang?
And then we took the road from NASA Goddard to the Space Telescope Science Institute, where Alex and Carl showed us the exquisite Southern Ring Nebula, a mixing bowl of stellar matter around a pair of dying stars.
Yeah, and I'm just blown away by the level of detail we can see, like in the outer part of this nebula. It's incredible.
You thought that this mission was
okay. After that, it was off to Germany, where the European Space Agency wowed us with pictures of galaxies interacting and mixing together.
Right, and this image, again, it's incredible because it's showing us one of these fundamental processes of the universe, how galaxies merge together, and we're able to learn about these processes in a brand new way.
So the Webb team has a lot to cheer about right now. So across the campus, there's this big watch party, and we can feel the excitement all the way from over here. So let's join that celebration now. We're back with Senior Project Scientist John Mather, along with the head of NASA's Science Mission Director, Thomas Zurbuchen.
So many people who worked so hard for so long to make this possible.
For everyone on Earth, this is your telescope. This is the largest, most powerful observatory ever put into space. It's the product of thousands of people working for more than 2 decades. This is a mission that's singularly focused on the biggest questions in science.
So, John, we looked around the world and we're the only ones with a cheerleading crew right over there. This is amazing. Look, you've been with this mission for decades. How do you feel today?
I am so thrilled and so relieved. This was so hard, and it took so long. It's just impossible to convey how hard it really was. We risked so much to say we're going to go do this, and it's so near impossible. But we did it.
There's thousands of ways this can go wrong. Many of them, we worried about and frankly feared even after launch. I have to tell you, I was really really, really nervous. And, it's almost like athletics for me. You always get to know the team when they're on the field. And on the field, they were right after this launch, and they were perfect.
They absolutely were. And I really wasn't worried, but maybe I should have been.
When the Webb telescope needed more resources,
that's difference between the two of us. I always worry. I always tell everybody I'm paid to worry, frankly, and that's good. What we want to do, though, is just really thank the team again. Of course, we heard Bill and Scott and Greg talking about the team that is there. I think what's also important is to recognize that Bernie is sitting there. He was the first manager. I was sitting there. Could you stand up?
Travelers from around the world. We have so many extraordinary collaborators. So let's begin with the partners who will be sharing the stage with us today as we reveal Webb's.
And I want to mention that Phil Sablehouse, who was a manager also during a time, is no longer with us, but his heart is with us today.
Yeah.
I see Katie in the background there.
I have to tell you, John, after each one of these milestones, I called a lot of people. I called Bernie, for example, and I called people at my job and people who are administrators, because there's many of them. And I just wonder how you feel about the team. Just give you the word here.
I am just so thrilled that we had a privilege to assemble such a brilliant team. We drew from the best of the best. And here we are. So my extreme deep thanks go to all the people who built that team. Not only to Bernie, who started us and helped us build up all the technology, to Phil, who made sure we would have a plan, and then when we didn't have quite enough money, to Bill, who pulled it all together and made it get all the way to the end. I am so thrilled that we have so much talent to draw on.
Welcome to NASA.
And here we are, we have the support of the country and the world to take on this immense challenge.
You know what I'm most excited about? There's tens of thousands of scientists, and frankly, some of them just got born or not even born, who are benefiting from this amazing telescope, because it will be with us for decades.
It will be. It took us about 25 years to get here, since 1995, and we have at least 25 to go, I hope.
So look, we are in a sense of these images, the art that is out there in the sky, revealed for the first time. We're thinking of the team, and we're thanking them. John, thanks to you, thanks to all of you, and back to Michelle.
Hello, Vermont. Hi, everybody. Nice to see you. Thank you so much, Thomas. And this entire collection continues to just absolutely astound me. Okay, Amber, so here it is.
Hello.
Can you walk us through the final image reveal?
Yay. Really nice to see you guys. Here we go.
Okay, and just one more for now.
The last image is
giving me hugs.
Look at that.
Okay, we also have Vancouver, Canada. So, Amber, can you tell us a bit about what we're seeing here?
Of course. This stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. Today, for the first time, we're seeing brand new stars that were previously completely hidden from our view.
Hello, there's something you want to point out here?
Absolutely. So, honestly, it took me a while to even figure out what to call out in this image. There's just so much going on here. It's so beautiful. One thing that really stands out to me is you sort of get this sense of depth and texture from this new data. There's a lot going on. To call out a few specifics, first of all, in general, the Carina Nebula is a nearby star-forming region within our own Milky Way galaxy, about 7,600 light years away. And in this view, we see some great examples, first of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars. We even see some galaxies sort of lurking in the background up here. We see examples of structures that, honestly, we don't even know what they are. Like, what's going on here?
So hopefully you can tell
the data is just so rich.
Okay, so let's do this. And there's something really special about the infrared. Infrared can actually see deeper into these star-forming regions.
Absolutely. That's one of the great things about infrared, is it really does reveal what's going on here in a really cosmic sense. And in general, what's happening in sort of this overall landscape is we have these gigantic hot young stars up here to the top of this rim, and the radiation and stellar winds from those stars is sort of pushing down and running into all of this. This is gas and dust. And of course, we know that gas and dust is great raw material for newborn stars and baby planets. But there's a flip side to this story, and also a little bit of a mystery, because these same processes can serve to sort of erode erode away this material and stop star formation. So we have this sort of delicate balance going on of new stars being formed, but at the same time the star formation is being halted. And for me, when I see an image like this, I can't help but think about scale. You know, every dot of light we see here is an individual star, not unlike our sun. And many of these likely also have planets. And it just reminds me that, you know, our sun and our planets and ultimately us were formed out of the same kind of stuff that we see here. We humans really are connected to the universe. We're made of the same stuff in this beautiful landscape.
And actually, the Carina Nebula was one of my favorite images from Hubble. So Hubble looked at this as well, right?
Absolutely, yeah. The Hubble image of this is also spectacular. We saw it in a different kind of light when Hubble took an image of this particular nebula. And then you can see amazing things with Hubble, but when we zoom into this new image, we're able to see so much more detail. And of course, all of us, you know, I grew up on Hubble, and all of us love Hubble. And I'm so excited to see what these two amazing observatories are able to do really in tandem with each other.
Thank you so much. And again, congratulations. It's been a pleasure to be working on this with you. I'm just amazed by what's been going on.
Thank you.
Yep. What is that?
So as we're wrapping up, one of the things that I really have to say is the journey that we've been going on is so very dramatic for me. So we've gone all the way from the birth of stars, and we have all the way from the distant galaxies to the birth of stars. This is where we all began. This was the whole point of the James Webb Space Telescope, to figure out our origins in the very, very early days of the universe, to star and planet formation very nearby. So right now I'm very honored to have our last special guest. This is the administrator of NASA, Bill Nelson. Honored to be with you, sir.
We have this sort of detailed
what a pleasure. What a banner day.
And this was not a long
It's clear that Webb represents the best of NASA.
Holder, right? The Hubble
it maintains our ability to propel us forward.
And it was just imaging.
For science.
With Webb, we took that image
risk-taking,
before breakfast. The
for
amazing
inspiration.
thing about Webb is the speed at which
and we don't
want to
ever stop exploring the heavens, nor stop daring to take another step forward for humanity.
Discoveries like this every
In the words of the famous Carl Sagan,
so thank you so much for joining us.
Somewhere,
it's been an honor to be working with you. Congratulations on all your hard work.
is waiting to be known.
It's so wonderful to see it pay off.
I think those words
thank you, and I'll see you later on today, I hope. So
reality.
Enjoy the day. Absolutely.
Thanks, Michelle.
So from
an
honor to have you here. Thank you very much.
Our eye to something a bit closer.
Wow.
It's a planet,
so,
but not one in our solar system.
This is a celebration for all humanity. If you've ever looked up at the night sky and wonder, whoever you are, wherever you are, this is your telescope.
Wasn't even part
and we also salute the thousands of people who have dedicated part of their lives to making Webb a reality. I also want to give a big shout out for the superb media team who is helping Webb's story to the world. This broadcast is a joint effort of the superstar producers, animators, and social media specialists at the Canadian Space Agency, ESA, NASA, and especially the Goddard Space Flight Center. Webb captures light in distant colors that the eye can't see, and you've actually made this visible to the world. So finally, if you go to nasa.gov/Webb-First-Images, you can download all of the images and data we just shown in full resolution, and check back often. From now on, we share new discoveries for exciting new destinations around the universe. July 12th, 2022 marks a huge day. Sorry for the brief pause. It's only just the beginning. For everyone at CSA, ESA, and NASA, I'm so very pleased you could join us. I'm Michelle Fall. Go Webb. Okay, I apologize. We're having some trouble with the signal from Canada. But luckily for us, we have an exoplanet expert right here, just in case that happened. So this is Nicole Colon, and she's an exoplanet scientist at NASA. And we're going to talk about some amazing new results from a very hot planet, I understand about 1,000 light years away. Absolutely. So talk us through what this discovery is and why this is so significant.
Well, this reveal that you're going to see is going to show the first spectrum of an exoplanet as taken from the Webb telescope. And this is exciting because it covers infrared wavelengths of light that we have not had access to before. So we've been able to use other telescopes to explore exoplanet atmospheres indicators in the infrared, but not to this level of detail. And this is just one sliver of data that Webb is providing us using the nearest instrument specifically.
And there's something about infrared that is actually particularly good for the spectrum. So in this case, what we're doing is we're actually going to take the light and break it up into a rainbow and look very, very carefully at how much color is coming in each part of the spectrum. So I believe we have that image. Can we put that up?
Okay, yes, I believe we're revealing the spectrum right here. So we now have our spectrum, and this is exactly what you're seeing. As you just described with spectroscopy, what we did was we observed a transit of an exoplanet. We observed the planet as it passed in front of the star. Now, mind you, this is not a direct image. This is an indirect image. So we've seen the effect of what happens when the planet and its atmosphere passes in front of the star. The starlight filters through the atmosphere, and then you can break that down into wavelengths of light, and you get a bunch of what looks like bumps and wiggles to some people, but it's actually full of information content. So you're actually seeing bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
So we have the spectrum up here. Is there anything you'd like to highlight particularly?
Yeah, absolutely. So we have several features marked here. So I call them features. They're these, what I just referred to as bumps and wiggles. But what you're seeing here is a telltale signature, the chemical fingerprint of water vapor in these atmospheres, in the atmosphere of this specific exoplanet. And the other thing we can tell actually is that there's evidence of clouds and hazes because the water features are not quite as large as we predicted. So we can take that and infer that there are presence of clouds and hazes.
Now, one thing that we really want to make sure people understand is with this particular planet, this is a hot world. It's actually closer to its star than Mercury is to our sun. And so we're not looking at liquid water. So we're looking instead at sort of steam, water vapor.
Yes, this is an exoplanet. It's about the size of Jupiter, about half the mass of Jupiter. It orbits around a sun-like star, but it does it every about 3.5 years. So it's extremely hot, extremely close to nothing like our solar system planets. But that's okay, because what we're seeing is, again, the first exoplanet data from Webb, and this is just the beginning. We're going to start pushing down the further, smaller planets and being able to take measurements just like this with the nearest instrument that was built by the Canadian Space Agency. But also, there's three other science instruments that will add to our knowledge in the infrared, as well as direct imaging of modes, along with the transit method. So there's a lot more to come.
I guess one thing we should mention is not only are we going to be looking at planets that are more like the Earth in the future, but we'll also be looking at planets in our own solar system.
Absolutely, yes. We're going to have exciting data from planets in our solar system, from Mars, outward, as well as asteroids and comets. So stay tuned for a lot more to come.
Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. So we have 3 more big image reveals, and with that, new and more exciting science. But first, let's take a look back at the journey that brought us to this moment. Celebrations like this one are only possible with years of hard work from a cast of
Hello,
thousands.
everyone, and welcome to our media briefing today for the James Webb Space Telescope, an international mission led by NASA with our partners, the European Space Agency and the Canadian Space Agency. My name is Elise Fisher. I'm with NASA's Office of Communications, and we are here live today from NASA's Goddard Space Flight Center in Greenbelt, Maryland, where we have just released the full set of the first full-color images and spectroscopic data from the Webb mission. So we have a panel of experts here to answer your questions today about the images and the data that you've just seen, as well as what that means for Webb's ability to explore the unknown in our universe. But first, I would like to turn it over to Eric Smith, Webb's program scientist and chief scientist of our astrophysics division at NASA headquarters, for some opening thoughts.
Thanks, Elise. Well, this morning we saw the amazing data that Webb has given us. We certainly thank all the scientists and engineers who have spent decades developing this amazing machine. It is now the science community that must take this unbelievable instrument we have been given and turn it into knowledge. Another thing you probably got out of this morning's briefing was that there are discoveries in these data, and because they were more or less practice runs with the instruments, we're making discoveries and we really haven't even started trying yet. So the promise of this telescope is amazing. And of course, as Elise said, we couldn't have done this at NASA without our partners in the European Space Agency and the Canadian Space Agency. I want to thank the scientists who have been supportive and patient for the many years that it has taken us to put Webb together. I know you will be happy with the results that you get out of it. Equally important, this is a telescope for the world, and that's why we want to have you part of the story that we tell everyone. It's important to get this out. The world's vehicle for deepest space exploration is open for business.
And so you don't want to build one that's just incrementally better than what you've got.
So with that, we will begin to take questions, and I'd like to introduce our panelists who are here to address them. In addition to Eric Smith, we have Nicole Colon, Webb Deputy Project Scientist for Exoplanet Science here at NASA Goddard. We have Christopher Evans, Webb Project Scientist for the European Space Agency. Klaus Pontoppidan, Webb Project Scientist for the Space Telescope Science Institute. We have René Dayon, Principal Investigator for the Near-Infrared Imager and Slitless Spectrograph, or NIRISS instrument, aboard Webb with the University of Montreal.
If you're just joining
we have Amber Strawn, Webb's Deputy Project Scientist for Communications here at NASA Goddard. And finally, Jane Brigby, Webb Operations Project Scientist, also here at NASA Goddard. So we are going to take questions today, both here in the room as well as from media who are on the phone lines calling in from around the world. So we have two members of our team who will, if you raise your hand, provide a microphone for you to ask your question. And we'd ask that when you do so, you please let us know your name and your outlet as well. And if you do know which member of the panel you'd like to direct that to, please feel free to note that as well. So let's start with some questions here in the room.
But actually, before we get into the amazing images, we're going to talk a little bit about where we are.
Thank you.
We're sitting here outside of the
Associated
Mission
Press.
Operations
Two questions, if you don't mind.
Which is the
first
key
for
central
Nicole.
hub for Webb.
For the average person who sort of was hoping to see a picture of an exoplanet, instead we see the spectrum. Can you tell us why that is so interesting and important? What it really, why is that better than a picture, and what does it tell you? And for Eric, if we go back to last night's deep field image, or someone else's better prefers to answer this. I know, is it too early? It's too early to say how far back this shows. Can you give us a range? Since you're saying this is further and deeper,
we solicit proposals from astronomers across
I keep
the
hearing
country
more than 13 billion. But you've had more than 13 billion before. So where are we looking? Are we looking at 500 or 600 billion after? 500, 600 million after the Big Bang, or what?
When the data come down and astronomers analyze their results, we are the lucky ones who get to share that data.
So with the exoplanet transit spectrum that we released today, which came out of NIRISS instrument, which René Dayon is the PI, I just want to make sure we acknowledge him as well. That spectrum is definitely an indirect method, right, of how we study exoplanets. And the thing is, compared to direct imaging, so Webb will also do direct imaging and take some pictures of known planets. And it will also search for as yet undiscovered planets with direct imaging. But in this case, we know that at least for cycle 1 observations, the first year of science, transit observations are a heavy part of the science program. So this first image or spectrum really represents what the community has proposed so far. And a lot of the direct imaging capabilities, though, they'll be demonstrated over the next year. And then that will also be a big part of Webb's story moving forward.
From which we had to select only a handful.
I'll start on the field question, and then I'm going to toss it over to Jane, who's the real expert on that. We know from taking spectra in that field that there's at least one object that is 13.1 billion years, and that's how long the light has taken to get to us. So we know from other data, Hubble and whatnot, that we can see a little bit past that 13.4, 13.5. So what this tells me, though, is that Webb, again, practicing with Webb, we almost got there to what Webb was built for. So when we do a program specifically designed to look for those farthest objects, we will get there. And I'll let Jane elaborate.
Yeah, so the spectroscopic redshifts that we got in that field include
basically
a redshift
translating
8.5,
light
so that's
that
the
we
look
can't
back
see
time
light
of
we can see
13.1 billion years.
Color,
And what's
like
remarkable
red,
is
green,
just
blue
how
to the different
good
filters
the
that we have
spectra
from
are
them.
without.
And the reason we want to color the
gradations. You
images
just,
is because
oh my,
there's actually
okay, there
more
you
that
go.
you can get,
I mean,
more
we're
information
used
that
to
you can get
barely
from the
being able
image
to
if
tell
you
the
see it in
redshift,
color.
and instead we have a
So it's a
spectrum
matter
that
of
has so many
picking and
lines.
choosing filters
You can say,
and
oh, I can
colors
tell you how
that
much
enhance the
how many
details
oxygen
and the
atoms there
structure
are
in the
in that
images.
galaxy. And so, yes, it's not the record
The
holder
shortest
because
wavelengths
we're
of
just
infrared
getting
light
started.
assign
This
those
is the
blue
proof that
colors,
it works.
and then
and
move
that
our
when
way
we
down
take these
to
kinds
green
of
and
data,
red as we go to lower
it
and
goes
lower
really
wavelengths.
deep.
And
As
then
far
we
as
additively
deeper images
combine
than
those
the
together to get our full color image.
you know, that's based on examining the images and
But there
figuring
is a
out
lot
what
of
is the
aesthetics
deepest, what's
that
the
are involved
faintest
in this.
blob that we're seeing.
Painstakingly going
And we're
through and cleaning
confident
these
that that's
images up,
deeper than images that Hubble
with
has taken
an
in the
attention
same
to detail,
wavelengths.
a level of detail
I mean,
like
honestly,
at the
it's
pixel
not hard to
level
do that. A
in
couple
every image.
hours and you beat Hubble in those wavelengths.
So when I'm working on the astronomical data,
Just to follow
it
on from
is
James,
this sort of
so,
marriage between art and science.
We
When
could
you're
see
choosing
one of
colors
the
for
first spectra was
filters,
shown in the
you
broadcast,
really are trying
and you'll see in the
to show
products
different
that we've actually
details
used the
and
near
processes that are happening
spectrograph,
in
the multi-object
astronomical
capability.
images.
So we have this
But at
deep
the
field
end of the
taken with
day, you
NIRCam,
want it to be very
and we can
compelling.
use
You want it to
the
be very
near spec
beautiful.
multi-object
The space is
spectrograph that
beautiful.
was one of the ESA deliverables to observe more than one galaxy at a time. So we can really make the most of this precious observing time. And I think there was 48 in that first test, and again, we'll be doing this, following up these deep fields with this capability to get the spectra of tens of galaxies each time, and those lines just pop right out, and you can do things we couldn't imagine of just last week.
If I may add, this target is very special because it was observed by all four science instruments. For example, NIRISS has a mode to do like NIRSpec to take spectra, but in this case it takes spectra of everything with slightly less sensitivity, but instead of a few kinds of objects you can observe, there's thousands of objects in one shot you can observe. And so, so this galaxy clusters represent this very tight and strong synergy for all four science instruments working together to answer one fundamental question, the origin of the universe.
Great, thank you all. We can take another question here in the room.
And when we saw the first color images, we knew that.
Hi, this is Issam Ahmed from AFP. Maybe for Eric, two questions. Maybe the first one is,
we are ready to
or
see
for
Webb's
Amber, I'm not sure.
image.
What are there any interesting scientific questions thrown up from the practice images we've seen so far? Are there any kind of lines of investigation that you would want to pursue on the basis of what we've just seen? And the second question, maybe, I don't know, Klaus, just for the public's knowledge, how long does it take to sort of process these spectacular images from infrared into these kind of really colorful, beautiful photos we see, and what does that involve? Thank you.
Wow. Okay.
I'm going to let Amber go ahead and take that
a
one.
near infrared image on our left.
With the deep image, of course, the first thing we think about are those very, very distant galaxies, like Jane describes in the rubies, scattered across that image. I study star-forming properties in sort of intermediate redshift galaxies and also galaxy morphologies. And for me, the first thing that stood out about that image, in addition to the little red dots, which are great, but was just the astounding detail that you can see in some of these galaxies. You can see star-forming regions in what are almost certainly very distant galaxies, and you just, they just pop out. There's just so much more detail. It's like, we've used this kind of corny acronym, but it's like seeing in high def,
and this
right?
foaminess is showing up in
and
orange
just the detailed morphology structures that we see in this image, it's fantastic.
Just lighting up the gas and dust of this nebula.
So I think on average we spend probably a couple of weeks on each image end to end, from actually getting the data on the telescope, downloading them, and then processing them through this whole process before we got what you see on the screen there. There's a lot of stuff.
So there's also
rays
in the outer regions that
we know that we're sort of the first science users, like the first people who had to actually take data from the telescope and create a product that we can do science with that is such high quality. If you look at the images, but also when you zoom in on it, and you zoom in and you look at details, that every detail you see is going to be real. And I just wanted to highlight as well for the NIRSpec spectra that we've seen, those amazing spectra that others have talked about.
Color.
Those were only taken at the very end of June.
Kinds of physics going on here. So we're actually seeing
so
in the blue.
In that case, we only had a few days to get those spectra. So this is still a testament for how powerful this observatory is. You can get quality of data that you can turn around. For the first time, we're doing this for science, right?
Molecular hydrocarbon actually forms on the surface of dust grains. so again, as we move inward, we see that the inner region is again hot ionized gas, but now it glows red because that's where it emits the strongest for mirrored wavelengths.
Hey, thanks a lot.
As we go into the center,
Bill Hartley,
we see kind of the surprise for
this,
us.
I'm not sure who to ask this, maybe Jane or Amber.
But we
can you talk about
didn't really see much
when you saw the actual data and your impressions or your anticipation going in? What I'm trying to understand your reactions as both astronomers and human beings to seeing this thing turn this dream into reality for you. In other words, did it match that?
And I think
did
that
the reality
there's
match
another
the
Easter
dream?
egg you want to
Do
tell
you
us
view
about?
this as an incremental step forward for astronomy, or is it, the kind of revolutionary step that Hubble was back in the day? Can y'all just give us a little perspective on
structure? And it points very much to the central sources. So I thought, oh, this must just be a density.
So I'm one of the 3 commissioning scientists, so I've seen
I thought that
a lot,
very strongly,
maybe most of the data that's come down during the 6-month commissioning period. And I will say that for me, earlier than this, that the first focused images that we took, where they were razor sharp, that for me was the one where I had the very emotional reaction of, oh my goodness, it works.
So I lost the bet.
And it works better than we thought.
You lost the bet, but
and
you got
shortly
these
after that, we
gorgeous
got a standard
images,
star, so we could measure how much light was going through the telescope. And that's not pretty, it's just a star, but like, oh my gosh, it really does work. And so for me, definitely, it was the...
Back to you, Michelle.
I think, personally, I went and had an ugly cry, okay? Because it works.
Thank you, Alex and Carl. And I have to say
what
that
the engineers have done to build this thing,
so
it is
you know,
amazing.
All over the world
we have an amazing engineering team, and across the board, we beat spec.
Webb's first science images.
Some of those engineers are in this room right now, Mike Menzel and his team. Like, they beat spec again and again and again. So I will say, first, it was a combination of giddy in the room, looking at the data, oh my God, this is great. And then, like, going and having a little sob, because it works. As far as what does this mean,
I guess nothing.
The first thing I did when I came on this project 11 years ago was I made a plot of how deep does this telescope supposed to go versus what does everybody else do. And because nobody had made that plot, it's like I'm just trying to wrap my head around it. I was like, oh my gosh, we're 2 orders of magnitude more sensitive than other telescopes, and it goes to 3, right? Like, okay, how could you not discover stuff if you're 100 times more powerful than previous telescopes? So from what the data that I've seen so far, from the work that we've seen in commissioning, which is all commissioning data, and then this first week of science. Yeah, this is going to be revolutionary. These are incredible capabilities that we've never had before.
They're jumping up and down.
Yeah, I'm also the part of the commissioning team as PI of the FGS and nearest instrument provided by CSA. And I'm a scientist, so I've been working on this project for 20 years. So we should expect what we saw. But no. Several times in the last 6 months, I nearly break my jaw of what I saw. These incredible images, the first transiting exoplanet spectrum in front of me, coming right out of the box of the data, was just amazing. And so, and I think our fellow scientists will feel the same thing when we look at the data. These data are just amazing. I think it's fair to say that today we're turning the page. It's a cliche, but it's true. We're turning the page on several new chapters on exoplanet, atmosphere, the early universe, star formation, you name it. And we don't even know what we're going to find.
There's also a big watch party right here on the NASA Goddard campus.
We can take another question
from the mission itself, and we also have top NASA leadership and representatives from our government. So hello, hello, watch party at Goddard, yay!
Thanks. Jeff Faust of Space News. I know the early release observations are designed to showcase the broad scope of what JWST can do, and I know one of the important areas of science for JWST is solar system science. So when can we expect the first solar system images or spectra from JWST?
Aspects of this project, including Webb's spectacular launch on the Ariane 5 rocket last December.
I'm very pleased to turn over the show there have already been solar system observations taken, and so those observations will be released Thursday, along with the rest of the commissioning data. So that's when the public will see the first ones. And we're very keenly aware that this is an important science area for the observatory. We also very confident we know that that we can produce wonderful, beautiful data and images for this. And so I actually have no doubt that we're going to see spectacular things from the solar system soon. It was just an early decision made for the early release observations that we didn't want to have to count on the moving target observations working with it, keeping things not too complicated. As it actually turns out, we probably could have done it, but
I have two very special experts with me, both scientists from the Space Agency.
We will come back to questions in the room in a moment, but we actually on the phone lines have media who are live at the Canadian Space Agency headquarters in Quebec. And so we have some media questions on the line that we can go to now. So I'd like to ask our operator to please provide instructions for our phone media to ask questions and take our first question there.
For a long time, so we're very grateful to have you with us. Thanks, folks. We are excited to reveal our image with you, but before we do that, we thought we'd give you a little bit of background because we've come here today because these guys were the first ones to pick up the signal during the Webb launch, when Webb first launched. They run a system called S-Track, which is NASA's deep space tracking system, and they were listening out when Webb called home. And the controllers here have been looking after a whole very, very impressive list of missions since 1968. ESA has played a very, very important role during the Webb Space Telescope. It provided the launch on board the awesome Ariane 5 launch vehicle from the Guiana Space Center. The atmosphere in the Mission Control Center was electric. I can tell you I was there.
Already begun. We have already taken data for scientists to one time in the first year, and those data will be released to the principal investigators of those programs in the next day or two, and some of them are public actually, so it will be